So, good day everyone. I am John Vincent, and today I'll be making a reflection video about what I learned from the 5 videos I've watched, which is the chip manufacturing, why chip making is so hard, photoli- photolithography, and how CPU is made, and the future trends of the computer engineering professions. So, these videos show me how technology we use daily, from smartphones to laptops, and it begins as a simple grains of sand. So, and through science and engineering, it becomes the far powerful microchips that shape our modern world. So, as I've watched these videos, I realize how complex, precise, and inspiring the process really is, and how it connects deeply to the future of the computer engineering. So, first is the chip manufacturing. So, the first videos, chip manufacturing showed how the journey of a microchip begins with one of the most abundant materials on Earth, which is the silicon from sand. So the silicon is purified, melted, and shaped into a single crystal called an ingot. Is what you called. This ingot is sliced into thin circular wafers, which serve as the base for chip fabrication. Each wafer is then processed in clear rooms where the air is filtered thousands of times per minute to remove the dust. So, because even a microscopic particle can destroy the delicate circuits. So, what amazed me most is how tiny features, which only a few nanometers wide, can be drawn onto this wafer through multiple steps of photolithography, etching, doping, and deposition. Through dozens or even hundreds of layers, engineers build transistors and metal lines and insulating layers that from the integrated circuits. So it made me realize that chip manufacturing is a combination of an art and science, requiring not only advanced machinery but also brilliant minds that can think in microscopic detail. So next video is the why chip making is so hard. So the second video explain why chip making is so among the most challenging and expensive engineering processes on earth. So making chip isn't just about drawing circuits. It's about creating features smaller than a few nanometers. So which is smaller than a virus. The complexity lies in how small, precise, and clean everything has to be. So the factories that produce these chips, called fabs, or cost billions of dollars to build. Um, the air inside must be hundreds of times cleaner than a hospital. So because even a single speck of dust could destroy a chip worth of thousands. So one of the hardest parts is shrinking transistor sizes as technology moves from 10 nm to 7 nm to 5 nm and now is 3 nm. So the quantum effects start to interfere. Electrons can tunnel through barriers and materials begin to behave unpredictably. So the videos also explain that each chip designs takes years to research and billions to produce. This is why um, only a few companies like TS, TSMC, Intel, and Samsung can manufacture the most advanced chips. So I realized how much precision, innovation, and teamwork are needed, and how this field pushes the limits of what is scientifically possible. So for the third video, which is the photolithography, which is the art of using light to build circuits. So the third video focus on one of the most fascinating processes in chip productions, which is the photolithography. So in this step, a wafer is coated with a photoresist, which is a special light sensitive material. Then a ultraviolet light is projected through a mask that contains the pattern of the circuit. So where the light hits the photorest reacts chemically and the unneeded parts are washed away. So this leaves behind a precise pattern that defines where transistors, wires, or insulators will be placed. It's like a printing an entire city map, but at the nanoscale. So I also learned that the newest generation uses extreme ultraviolet, which is the EUV lithography, which uses very short wavelengths of light to print even finer patterns. So this process must be done with perfect alignment, often hundreds of times per wafer, to create multiple layers of transistors and connections. So what struck me most was how light and chemistry, which has two simple scientific concepts that come together to form the most complex structures in existence. It made me appreciate how interconnected all areas of science truly are. So, for the fourth video, which is how a CPU made. So, the fourth video gave me a detailed look how a central processing unit, which is the brain of our computers, which is created. So the process starts with the silicon wafer, and through repeated steps of oxidation, photolithography, etching, and doping, millions or billions of tiny transistors are formed. So each transistor acts like a switch that can turn on or off, which representing a binary 1s or 0s. So these are groups into logic, gates, and circuits that perform a computations. So um, one key part of this process is doping, where specific impurities are added to to the silicon to change its electrical practice properties. So these two processes is these two doping, which is the N type and the P type. The N type doping, which is with the elements like the phosphorus, which adds extra electrons, creating negative charge carriers. So for the P type doping, with elements like a boron, creates holes or positive charge carriers. So by combining N-type and P-type regions, engineers form PN junctions, which are the foundation of transistors, especially the MOSFET or MOSFETs, which is the metal oxide semiconductor field effect transistors. So each transistor has a source, drain, and gate. When voltage is applied to the gate, it controls the flow of current between the source and drain. Billions of these transistors are combined in CMOS, which is the complementary MOS technology to make a CPU. So after the transistors are made, so metal layers are added to connect them together into a working processor. So the chip is then tested, cut from the wafer, packaged, and mounted onto circuits boards. So this made me realize that however CPU we use represents years of design, testing, and manufacturing mastery. It's a human ingenuity turning sand into intelligence. So for the last video that I watched, which is the future trends of the computer engineering professions. So this final video that I watched is look toward the future of computer engineering. It discuss how emerging technologies are redefining the role of engineers and the direction of innovation. So some key trends mentions in the video are artificial intelligence and machine learning hardware and quantum computing, edge computing and Internet of Things, which is the IoT, 5G and the future communication networks, nanotechnology, advanced materials, cybersecurity and ethical AI, green and sustainable computing. So, artificial intelligence and machine learning hardware is a chips especially designed for neural networks and AI training. And quantum computing, which uses qubits to process informations in ways that classical computers can't. So next is the edge computing and the IoT, which is the Internet of Things, bringing computation closer to where data is collected. So 5G and the future communication networks, which allow faster data transfer and the real-time applications, nanotechnology and advanced materials, which continue chip scaling beyond silicon. So cybersecurity and ethical AI, which is focusing on data privacy and algorithms fairness and responsible of computing. Next is which is the last one, which is the green and sustainable computing, which is focusing on energy efficient and recyclable materials. So these developments show that computer engineering is not is not slowing down. It's an evolving into an even broader and more exciting field. Watching this video made me realize that the future belongs to engineers who can adapt, learn continuously, and think beyond boundaries. So, technology is moving toward intelligence, connections, and sustainability, and we have the responsibility to guide it wisely. So, after watching all these videos, I developed a deep respect for the invisible technology behind every device we use. So, I learned that making a chip is not a simple assembly, it's a fusion of physics, chemistry, computer design, and innovation done in one of the cleanest and most um, controlled environments on Earth. So I realized that computer engineering is not just about writing code, it's also about understanding the materials, circuits, and systems that make computation easier and possible. So these videos reminded me that even something as small as a transistor represents decades of human effort and creativity and discovery. So as a future computer engineer, I'm inspired to keep learning and explore how technology can improve lives, not just by making things faster, but making them smarter, greener, and sustainable. So that's all from my reflection video. Thank you for listening to my reflections, and I hope this inspired you to see technology not just as machines, but as a masterpiece of science and human passions. Thank you.